It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farming and Nice Coffee.
Hi guys, welcome to the next video. For this one I'm going to be talking all about equilibrium and in particular the Chatelier's principle. Okay, so what you need to do, particularly when you're looking at equilibrium, is make sure you understand everything that affects the rate of a reaction. Okay, because we're going to talk about rate of reaction and why particular concentrations of species changes. Alright, so make sure you watch that video first. So, equilibrium, the Chatelier's principle. Basically, the Chatelier's principle says that if the Chatelier's principle says that if a change is introduced to a system, alright, which is at equilibrium, right, the equilibrium will shift to counteract the change, and this is really the key thing. Alright, counteract. So if you increase the concentration, the equilibrium is going to shift to decrease the concentration. Alright, if you increase the temperature, equilibrium is going to shift to try and decrease the temperature. Okay, if you increase the pressure, equilibrium is going to shift to try and decrease the pressure. And so they're the ones that we're going to actually be having a look at. So make sure you understand and can remember that definition for the Chatelier's principle. So first thing is I want to talk about these three things. Okay, so we're going to talk about temperature, we're going to talk about pressure, and we're going to talk about concentration. Okay, and these three things, along with, and we'll talk a little bit just about catalysts at the end, these three things are really important in terms of equilibrium reactions. Remember, equilibrium reactions are ones where the rate of the forward reaction is the same as the rate of the back reaction. Okay, and when it's at equilibrium, there's no change in the macroscopic properties. That means there's no change in what you can see. Okay, so first thing I'm going to talk about is pressure and how that affects the rate of a reaction. Okay, when you increase pressure, okay, what you start to do is you start to squish your particles in closer. And so I showed that in the previous video on rate of reaction with the marbles, where we halved the area that they were in, and you can see we increased the concentration of them straight away. Same number of particles within a smaller space, so our concentration doubled in that case. Alright, so when you increase the pressure, because gases basically want to expand and take up as much room as possible, what the equilibrium does is it moves or shifts to counteract that increase in pressure. So what it will do is it will go to the side of the reaction which has the least number of gaseous moles on it. That actually decreases the pressure because you're reducing the concentration moles in there, so you're reducing the pressure back. So what you need to do is have a look at the stoichiometry numbers in front of your molecules that you're reacting. So here we've got carbon monoxide, and there's 2, and oxygen we've got 1. So overall on this side we have 3 moles. Okay, so here we've got 3 moles. Over on this side we've got 2 CO2, so we've got 2 moles on this side. So it's uneven. So if we increase the pressure of this, what's going to happen is our equilibrium is going to shift to the right to produce more carbon dioxide, because that's going to reduce the number of moles we've got in there, and that will decrease the pressure back down. So I've just shown here of what we've got initially for this reaction. So we started off with some carbon monoxide and some oxygen, okay? And initially there was a high concentration of these, so there was lots and lots of successful collisions occurring that resulted in carbon dioxide formation. So we can see we've got a steep slope, which tells us we've got a high rate of reaction. All right. Carbon dioxide forming, again, initially was fast because there was a high concentration of reactants reacting, okay? But eventually we get to a point where the concentration of all 3 species is constant. Now that's not saying that the reaction has stopped, but what it's saying is that the rate of the forward reaction of forming CO2 is exactly the same as the rate of the back reaction of the decomposition or breakdown of CO2. Okay? So we see no change in their concentration, no change in macroscopic properties. So we've established our equilibrium. Now what's going to happen if we just leave this to react? Okay? What's going to happen is we're just going to still get molecules of carbon monoxide and oxygen going forward to form CO2, and CO2 going backwards, exactly the same thing. But if we increase the pressure, what happens is that straight away we squish all these particles into a smaller space, so we increase the concentration. So all 3 of these peaks are going to jump up. And that's really important. If you see a graph like this, where all 3 of your peaks jump up at this point here, where we increase the pressure, all right, if you see all the peaks jump up, you know there's been a pressure change. Now what happens is the equilibrium shifts to the right towards the products because that's less moles. And so what's going to happen is we're going to use up some carbon monoxide and oxygen to form CO2. So our concentration of of carbon monoxide is going to decrease, and our concentration of oxygen is going to decrease as well. Now hopefully what you can see is that we've actually got a bit of a relationship occurring between these two. If this goes down by a value of x, this one up here actually went down by a value of 2x. Now that comes from the reaction equation, which makes sense. For every 2 moles of carbon monoxide we've got, we need 1 mole of oxygen. So it makes sense that when these are reacting, this is going to decrease in concentration at twice the rate of this one. Okay? Hopefully what you'll see, or be able to work out, is that the carbon dioxide is going to increase by double the amount. So that's actually going to go up by 2x amount. Okay? Until we get to a point where all the concentrations are are not changing, they're constant, and so this is our new equilibrium. Okay? So it's really, really important that you understand what effect pressure has of increasing the concentration straight away if you increase the pressure, or if you decrease the pressure straight away, all 3 of your graphs of your lines would drop down. Okay, then you work out what effect it has upon the number of moles, and you go from there. If we had 3 moles and 3 moles, increasing the pressure would do nothing other than increase the concentration of the mole straight away. Now that is beneficial because if you increase the concentration, you increase the rate of reaction. Okay, but because we've established our equilibrium already, all right, it doesn't really going to affect your yield. So that's the first one. That's pressure. Next one we're going to look at, okay, is concentration. Okay. So for concentration, this time what I'm going to be doing is I'm going to be looking at the reaction between PCl3, so phosphorus trichloride, and chlorine to give us phosphorus pentachloride, PCl5. Okay, so initially again we'll have some PCl3. Okay, so there's our PCl3. We've got some chlorine in there. Okay, and we're forming our phosphorus pentachloride like that. And at this point, what we've done is establish our equilibrium. Okay, so kind of exactly the same as before. Now, with concentration, you've got to remember with Le Chatelier's principle, if you increase the concentration, the equilibrium is going to shift to decrease it. Okay, so if we increase the concentration of PCl3, our reaction is going to want to shift to decrease it. Okay, and it does that by causing them to react to form PCl5. Okay. So, let's have a look at this again, going back to our marbles. Three, two, one. Okay, so what I'm going to use to represent my PCl3, my phosphorus trichloride, is this little blue marble. Okay, chlorine gas is our little red marble. Okay, what happens is when they react, we're forming our PCl5, which we're going to do is the big blue one in this case. Okay, so when we reach equilibrium, okay, what we've got is something like this. Okay, so we've got, let's say 4 of our chlorines in there, and we've got, 3 of our PCl3s, okay, and we've got 2 of our PCl5s. So this is our equilibrium, okay. We've got the same number in there. Now, what we will have happening is that we will have some red and blue colliding, okay, so these ones will collide, and they will form a PCl5. But exactly the same time as that is happening, one of our PCl5s is breaking back down into a Cl2 and a PCl3. So we've got this constant concentrations occurring here. However, if we change the concentration, let's say we add in some more of our PCl3, okay? So all of a sudden we've got a higher concentration here, okay? This upsets the equilibrium because we've increased the concentration here, the equilibrium wants to shift to counteract that. So what's it going to do? Well, it wants to counteract it by getting rid of some of this PCl3 that we've put in. How does it do that? It needs that to react with some of our Cl2. So our PCl3 and our Cl2 react to form PCl5. Okay? So what we've done now is we have reduced the concentration back down of our blue marbles, the PCl3. Okay? Notice what we've done is we've decreased the number of our Cl2. Okay? And we've increased the concentration or number of our big blue marbles, which is the PCl5. And we've re-established our equilibrium. So we can show that back again on the graph like this. Okay? So when we increased the concentration of our PCl3, what happened is that the concentration of that increased. So that's where we introduced, or we put in, more PCl3. Okay? And then what happened is that equilibrium shifted to try and reduce those blue marbles, or the PCl3. And so what happens is we took out some of that PCl3 again till we got back to a nice concentration. Now we took that out by reacting it with the Cl2. Okay? And just like in the previous one, what we've got here is that this decrease here, okay, is exactly the same as this decrease here. Okay? It's a 1-to-1 reaction up here, so they decrease by the same amount. What we did is we took one of those red marbles, one of those blue marbles, and we reacted them together to form more PCl5. So that has gone up by X amount because it's a 1-to-1-to-1 ratio. Okay? So changing the concentration, our equilibrium didn't like that. It shifted to counteract that change. So we increased the concentration of PCl3, or the blue marbles, and it shifted to decrease that concentration. Okay? It did that by reacting with the red marbles, the Cl2, so that concentration dropped down as well, and we formed more of our big blue marbles, the PCl5. Okay? So equilibrium now comes back to a point where we've re-established our new equilibrium here. Alright? That's our new equilibrium. Alright, final one I'm going to look at is temperature. So with temperature, what you need to understand for temperature is that if you increase the temperature, you're obviously going to favour an endothermic reaction. Okay, so what that means is obviously endothermic reactions are ones that require energy or take energy in. So if you're increasing the temperature, you're increasing the energy, which means you're going to favour the forward reaction. So in this case here, we've got some nitrogen, okay, and we've got some oxygen, okay, and they react, okay, to form some nitrogen monoxide. Okay, we establish our equilibrium at this point here. Now, what we're going to do at our new point over here, so I'm just going to extend these graphs a little bit. What we're going to do at this new point here is we're actually going to, in this case, decrease the temperature. Okay, by decreasing the temperature, the forward reaction here that we have is endothermic. So an increase in temperature favours the endothermic reaction. So a decrease in temperature is going to favour the exothermic, which is the back reaction. So we're going to form more N2 and O2. So as we decrease our temperature, the Chatelier's principle states that equilibrium will shift to increase the temperature. So if it does the exothermic reaction, it's going to let out energy. That's going to increase the temperature again. So our NO2 is going to decrease in concentration because we are using it up as we do the back reaction to it, which is exothermic, to increase the temperature again. So that's going to go down by 2x. Our oxygen is going to go up by 1x, and our nitrogen is going to go up by 1x again as well, until we establish our new equilibrium over here. Okay, so at this point here, what we did was we decreased the temperature. So if you see a graph where just the concentrations start to change, okay, without any sharp spikes, that's a temperature one. So remember, an increase in temperature favours the endothermic reaction, a decrease in temperature favours the exothermic reaction as it shifts to counteract the change. Final one I'm going to talk about is just catalysts. Now, catalysts, when we're talking about equilibrium, just they don't really affect the position of the equilibrium at all. So if we go back to our reaction pathway diagram, okay, you remember on here, our activation energy is this, okay. What a catalyst does is it lowers the activation energy here. So we get a lower graph, like this, with a lower activation energy in there. Okay, so it provides an alternative reaction pathway with a lower activation energy, and it helps line particles up in the correct orientation. So what that means in terms of a graph for concentration versus time is if we have a reaction, you notice we've got our reactants that go like this to form our products, and we have our products that go like this, okay, and we get to an equilibrium spot here where the slopes of both are 0, so there's our equilibrium. If we introduce a catalyst, all it does is allows equilibrium to be obtained faster. So you'll actually have your graph that looks like this. Okay, and what would happen with our our reactants they would go like this. And what we do is our equilibrium shifts to be back here. So what we do is with a catalyst we get a faster equilibrium. So those are the things that can affect an equilibrium position or equilibrium concentrations. So make sure you can go back and explain what effect temperature, concentration, pressure and a catalyst will have upon equilibrium. Make sure you can explain it in terms of the Chatelier's principle as well. Okay, thanks guys, hope it helps. See ya.